V's, if you have a dark matter, a heavy dark matter particle interacting with a nucleus here. If you have an elastic interaction with an electron, this kinematic constraint is going to give you a few EVs, which is extremely hard to measure. We'll talk about some corrections to this, but in general, this is the idea. We should also look at this A square enhancement. So as long as all the nucleons look the same to the dark matter particle, we expect in this in this area of momentum transfer to have coherence of the amplitudes over all of the nucleons, meaning that we have an A square enhancement of the cross section. So larger nuclei are supposedly more sensitive and have higher cross section for the same dark matter interaction with the nucleus, with the nucleon. Now, since we're looking at recoil spectra that are in the keV range, let's look on the left at what we expect them to look like. This is the normal WIMP paradigm. All of the spectra that we're looking for are in the very few tens of keVs and below, and they peak at very low momentum transfers. The energies we want to look for are keV-ish, but if we can go lower, we typically gain much more sensitivity because most of the events are still going to have small energy depositions. And this is less true for heavy WIMPs, which have a shallow spectrum, and more true for light WIMPs, which have very steep spectrum, but it's true for basically all of them. And obviously, this comes from a combination on the right of kinematics and the A square enhancement that we talked about. If you have a heavier nucleus, you have more recoils that are low energy and less recoils that are high energy. And this is, of course, depends on the mass of the dark matter. This is a classical WIMP of 100 GeV. We will see that this changes. Of course, there are ideas that could change this paradigm. Some inelastic dark matter, EFT operators, some other ideas that could give you a spectrum that is not peaking at zero, as we saw in the vanilla WIMP, but actually peaks at something well above, and then obviously the sensitivities are going to be different compared to between experiments and technologies. But this, I think, we're not going to touch too much. Just a quick, I think everybody knows that in the back of their mind, but if you're not directly in the field, you might forget it a little bit. So first of all, this is an exclusion or discovery plot. We have WIMP masses on the x-axis. We have the cross-sections on the y-axis, typically log and log. And what we have is usually, if we do not find in an experiment anything that looks like dark matter, we can draw a line that says that above that line, we reject the WIMP hypothesis or dark matter that could have interacted with that cross-section and that mass. And if we do find something, we try to have a confidence interval around that something. For instance, this fake signal contour, which tell us we find something and we believe this is where the parameters are, where they exist, where they can explain the signal that we've seen. And how do these plots change? So first of all, if we want to make them lower, to probe lower cross sections, we need to very simply increase the exposure. If we want to have something biting to the left here to lower WIMP masses, you can see that this is growing exponentially fast when we go to lower WIMP masses. We need low energy thresholds and smaller target nucleus. For instance, a heavy nucleus will be recoiling less when you have masses that are lighter than the nucleus itself. And we would like to have the combination of the smaller target nucleus and lower energy thresholds in order to bite to the left. And in principle, this also costs us with high mass sensitivity, but this is the ballpark. On the right, you can see how exposure with time affects the sensitivity. You can see that when you increase exposure, of course, if you have some benchmark detector, you're going to gain a lot by increasing the exposure, but then with time, you're going to be less and less and less interesting. That's because the sensitivity is measured in a log scale. Now, if you want to increase your sensitivity significantly, the main thing you want to do is increase the target mass or decrease the background, or usually both. There is discrimination between backgrounds and signals. I'll talk about this soon. And of course, you suffer if there is too much background, and then you have less and less sensitivity. So there is a compensation between exposure and background that you have to take care of. Now, many of you saw this. This is how much the field of direct detection has progressed in the last 20 years, 20 something. So from cross sections of 10 to the minus 40-ish centimeters square for interaction with the nucleon, we've come down to about almost 10 to the minus 47 centimeters square, which is very impressive. We had about 6 orders of magnitude increase in sensitivity for 20 years. And you can see that basically all of the, or most of the progress, and definitely all of the progress in the last decade has been done with liquid xenon. I'll make it more generally with liquid noble gases. And this is what we're going to talk about. The question is why and how and where it is going in the future. And this is what I'll try to answer. Now, we have to remember what backgrounds are. This is, I'm sure you know this. The backgrounds are composed of many, many components. There is one major component here. You can see this is a very old plot, but you can see that the dominant intensity of background particles when you are on the ground is coming from muons from cosmic ray air showers. If you want to kill them, you have to go very, very deep underground, and then you can kill them. The number is in the kilometers of water equivalent, or sort of a kilometer of rock. And this dictates that all of these experiments should go underground. There are, of course, other components, and they are killed a lot earlier. And then you are ended up with things that are already on the ground, or already in the lab, or already in the, and this is going to be the major effort to get rid of those. This is, of course, the underground scenario. You can see so the number of muons that reach each laboratory depends on how deep it is, and this is the set of laboratories that are actually available in the world today. Now, when we are already underground, we want to fight the backgrounds that we have. These are just a quick list of what kind of backgrounds there are. Gamma rays are going to be available from basically everything, because all of the things that you touch in life have some components of radioactive gamma emitting isotopes, and they are going to be penetrating. Those gamma rays are about an MeV, and MeV gamma rays can cross many centimeters of any kind of material. That depends on the material, of course, and the gamma rays. But that means you're going to see them in your detector. You need to shield it. You need to self-shield, which we'll talk about in a minute. Use multiple scatters, because gamma rays typically do not scatter just once. If they scatter once, they will very likely scatter again. If you can find multiple scatters, you can tell that this was not a dark matter particle. Of course, since we are looking for something that interacts with the nucleus, we would like to be able to separate that from a gamma ray that enters the detector, which usually does not interact with the nucleus, but with electrons. So if you can discriminate between electron recoil and nuclear recoil, that will help you a lot. Over that, you have internal alphas and betas that are not traveling far. So if a beta or an alpha is emitted outside the detector, you're not worried about that. It has to be done inside, and then in some cases it might be a very annoying background. One of the most terrible backgrounds that we have is neutrons, because neutrons interact with the nuclei, which is exactly what we're looking for, and we have to get rid of them. They come either from spontaneous fission of a very heavy element or from alpha N, alpha that interacts with the light nucleus and then emits an alpha N process that emits a neutron in the end. Neutrons like gammas also multiple scatters, so you can do that. You can wait for the neutron to slow down and then catch it, and then it typically emits several gamma rays of very high energy, and you can find them. This is called a neutron veto, and that's it. Neutrinos come from many sources. We'll talk about them, and of course there are always other backgrounds that we don't know before we start building an experiment. Now, one thing that is important for, especially important for novel elements, is internal electromagnetic backgrounds that are inside the detector. These are usually things that are mixed in the detector, like krypton 85, radon 222, argon 39, argon 37, and even tritium, the other elements that might be mixed. And we need to, first of all, find them, and second, try to get rid of them. This is a long story. Okay, let's skip this. Neutrinos can do basically two things that are interesting for us. First thing, they can scatter off electrons, and then they look a lot like Compton or beta. The most dominant source of this kind of neutrinos is the sun, of course. The PP neutrinos are basically all energetic enough to give us electrons that are in the energy range that we're looking for in dark matter. So this is a problem. The good thing about that is that neutrinos have a very, very, very low cross-section. So typically we are not worried about them. We start worrying about them when we have huge exposures, and actually this is the right era where things start to get interesting in those neutrino interactions. The second thing that neutrinos can do, so this is the neutrino still. The second thing that neutrinos can do is have a neutrino nucleus elastic recoil that is coherent. This is the diagram that is plotted here. You can interact basically exactly the same as we're looking for in dark matter, and then kick a nucleus, and in the detector they will look exactly the same as dark matter. They do not double scatter. You cannot find them with a veto, which means they are the ultimate background that we currently do not have any way of distinguishing from dark matter. Again, the good thing is that there are not many of them. You need extremely high energy because the neutrino is basically almost massless. In order to give enough energy to a nucleus, the neutrino has to be extremely energetic. The sun only provides one type of neutrinos that will enter our discussion today or in the near future, which is the B8 neutrinos that reach 13 MeV. And then they can give a kick that is at the very low end of the recoils that we're looking for. Higher energy neutrinos like supernova neutrinos or atmospheric neutrinos can actually do worse, but they are much less abundant. Now, let's go to where we are with dark matter noble element detectors. So first of all, for the next few slides are going to be very focused on the physics or on the properties of noble elements. There are 5 noble elements that are stable, and this is helium, neon, argon, krypton, and xenon. They have an evil sister, which is radon. It's also a noble element, but it is not stable, so you never have enough of it to actually have a detector, but you always have enough of it to produce a background. We'll talk about it later. As you can see, all of them become liquid at cryogenic temperature between minus 90-something degrees Celsius to minus almost 0 Kelvin, which is helium, 4 Kelvin. All of them have to be cooled down and held in a very specific range of temperatures and pressures, because we want to keep them liquid and not have them freeze and become solid. This is also something that was thought of, and building detectors from solids. We'll not discuss this today. The good thing is that you can have them at very high density. You can shape this liquid into whatever container you pull. You don't need to machine anything. You don't worry about putting electrodes. You just put the electrodes and you fill the liquid. It's like filling a glass. And this is a very nice property. Helium specifically has this transition to superfluid helium, which we will talk about in the end, which can be useful for a detector. And all these liquids are dielectric. So if you want to put an electric field on them, you can do that. If you want to put a light detector inside, the light detector is shielded electronically from its surroundings by this liquid, which is nice. And the chemistry of them, of course, they are noble liquids or noble elements. So they almost have no chemical interaction, which means you can clean them from anything that is chemically active rather simply, which is very, very useful for us. Now, the thing we use most is what is called scintillation. So scintillation, as opposed to atomic emission of light, is a very elaborate process that creates photons, and these photons help us detect actual particles. These things have been known for many decades. So let's talk about a particle that interacts with our medium. The medium is made of some noble element A. Now, here you see simulations of a particle that kicked a noble element. This is in Xenon specifically, but it would work for any of the others. You have a nucleus that is given a very high energy of, let's say, 50 keV, and then this nucleus is going to stop inside the material. The way nucleus stops, or an electron stops, is by ionizing many electrons on the way. It's not just ionizing. Some of them it ionizes, some of them just get excited, but you lose a lot of energy one by one on these many states, and you create ions along the way. Now here, every green point is an ion that was created along the way, the path of the nucleus. And once you created either an electron hole is a charged ion, positively charged ion, you can create a pair of these, or you can create just an excited state. You have recombination, and this recombination now creates usually an excited state, because the recombination doesn't go directly into the ground state. Those excitons, the excited states, are going to have a 3-body recombination and create a metastable molecular state. We'll see that in a second. This molecular state is going to be very loosely bound, but also very long-lived. So they live for a very long time, and then they decay. Their decay emits UV photon. The UV photon is less energetic than what is required to have the first excited state of the noble element. And that means that those UV photons are now going through a transparent medium because they are not able to interact with any of the bound electrons inside the medium. Now, if we want to look at how this is happening, we can see here that you can form a molecule of two. Here it's two xenon atoms. You have the same chart for helium, neon, krypton, and argon. And what you have is now the separation. We have two xenon atoms or two argon atoms, doesn't matter, and they are separated by some distance. And you can see that they have some shape of potential, which has a minimum around here. So this is a bound state. The bound state is not the ground state because the ground state is two separate elements. This is still a noble gas. Before you make this bound state in its own ground state, you start with an excited molecular state, and this molecular state was created when those two, the exciton was meeting friends that are neutral in the medium. Now here you're going to emit usually a number of IR photons. They are very, very long wavelength, but you need to emit them in order to go to the ground state of the molecule. And then this molecule is going to live for an extremely long time in terms of atomic physics. This is at least nanoseconds. And since the orbits here have two electrons that can arrange in either a singlet or a triplet, we actually don't have one ground state. We have two ground states that cannot mix, the singlet and the triplet, and they have somewhat different lifetimes. When they decay, they are going to emit a photon, and this photon is going to be, as we said, less than the energy that is required to excite the first excited state of a neutral atom. And here you can see, zoom in, right? You can see the triplet and the singlet energy curves as function of the separation. And here, of course, after you emitted this photon, the two nuclei are going to drift apart and become just regular unionized atoms. Now, the light that is emitted depends on the properties of this molecule and on or generally on the element. And you can see that it is in the deep UV. So this is the wavelength, this is the energy of the photon. So this is in EV. The lowest energy that you get is for xenon, which is about 7 EV. If you go to helium, you get about 16 EV photons and the wide spectrum. Now, any of you that saw spectra of atomic transitions know that this is something extremely wide. This is not an atomic transition. And the reason that it is wide is actually very clear from this. You have a very shallow potential of the molecule, and you have very steep change in the actual ground state separation. So the width here is dominated by several processes. The main one of them is the fact that you have a molecule in the ground state, and it is going into different final states. This is not a transition between two atomic states. And of course, this depends also on the density of the liquid or gas, but we'll not get into that. As we said, the singlet and the triplet are different, and they can have different lifetimes. The difference, for instance, in xenon is between a few nanoseconds and 20-something nanoseconds. In argon, it's between a few nanoseconds and over a microsecond, and this is getting even more significant when you go to helium, which has an extremely long lifetime for the triplets. I don't remember exactly, I think it's in the second. And this is something that can be used later for all kinds of detector purposes. Now,
can I ask you a question?
Yes.
So the way you presented it, the whole scintillation formation, it almost sounds like a two-body problem. Is this something that can actually be calculated ab initio, or is this all basically in the realm of experimental physics? I mean, you say that it's some dependence on pressure and so on. So of course there are some macroscopic environmental variables in this game, but I wonder how far is our theoretical understanding of the scintillation process?
So if you look now at the graph here, so the level of molecular physics of the excimers and their decay and their lifetime, we have a pretty good knowledge. The things that are not known are measured specifically by absorption spectra of excited states. This has been done for a few decades. Now, the tricky part is taking this atomic and molecular physics and putting it in what happens when you have, let's say, a nucleus decelerating inside a liquid. And there, when the energies are high, let's say tens of keVs and up, I think we are in a semi, how do you call it, empirical models, and they work fine. I don't know if you remember, you probably do. When you try to apply effective field theory or effective models, actually, not field theory, just effective models of what happens when a low energy nucleus is decelerated in a liquid, you can get sometimes orders of magnitude wrong. So the first calculations that try to estimate what would be the light yield, the actual production of these excimers in Xenon, like 12 years ago, claimed that below about 30-something keV, you're not supposed to get any of them. And we know that by measurements, you get them down to very few keV. So we're not at the level that you can do basic physics calculations from scratch and get to how many photons you're going to see.
Okay, so maybe to follow up. So on this table here, you say the cost per quanta. Is this now something empirical that sort of includes already this the recoiling nucleus inside the liquid? Or is this basically the on-site production of?
This is a very good question. The cost per quanta is the optimal cost per quanta. You basically never get it for nuclei, you get it for electrons. And this is what we use eventually for what we call the combined energy scale. I will show it. The strike down number here is how much it costs to produce one excited state, and which is not enough. You don't get all of it, so you lose some energy. But in principle, if you take argon or xenon and you give it a high energy electron, and you ask how many quantas you're going to get and combine both photons and electrons, this is approximately the number you're going to get. There are some debates about what is the exact number and if the number stays exact. But for what we know.
Yeah, I just wonder, because if I look at your plot here, where you have this H nu, right? So the 9.4 EV, that sounds, I kind of find that number between the sort of the excited levels and the ground state. So it seems reasonable. This is what you need to invest. But now if you go to 13, you're basically really high up in this excited states.
So the 9 here go. So these states are molecular states. These are not atomic states of a single electron.
So, but the quanta is a scintillation quantum, right? So it basically corresponds to one h nu that you draw there.
This one.
You say, yeah, but to get that out, you basically need to pump in on average 13 EV. So you're somewhere higher up, and then
you lost some of it. So some of it you lost to those IR photons, and some of it you lost to internal degrees of freedom, for instance, of the molecules, electrons that got thermalized and then maybe a lot later got recombined.
Okay, thank you.
Some of the energy is lost. You don't get all of it in photon. This is all right. So you get a 7 EV photon for every 13 or so EVs that were deposited. Pretty good, actually.
Okay, good. Thank you.
All right. Now, we talked about the singlet and triplet, but the singlet and triplet are an internal thing to the detector. And what you want to know is how they behave when you have a different interaction. So it appears that the ratio between triplets and singlets depends on the density of the ionization cloud and other parameters. And then there is a difference between how the temporal behavior of the scintillation signal looks when you have, for instance, electrons or alphas, or what is called fission fragments, the neutrons hitting the nuclei. And the different behavior can be utilized to differentiate between what kind of particle it was. Don't pay too much attention to this. This is with quenchers. So you can see that there is a big difference in argon. Maybe you don't find it big, but between electrons and what we will look for as nuclear recoil equivalent of dark matter, the ratio between the peak. So this is don't pay attention to the heights. This is just to separate them. These are arbitrary units, but you can see that the long tail of electrons is pretty much missing. This is a log scale, and this also happens in xenon, but the differences are somewhat smaller. Here you see a very big difference, and this comes from the fact that this is zero field, so there is no field applied on the xenon. So the electrons here are actually dominated by the time it takes to recombine, and not by the lifetime of the singlets and triplets. The singlets and triplets you can see here are rather similar, or not very far. Now, if we now go and look at what else happens, we said that there are ionization processes that happen while we create this cascade of scintillation. If we put some field over the area where the interaction happened, we are able to extract some of the electrons. Now, which electrons are we going to find? We find the electrons that went over the sphere of recombination and are unlikely to recombine by random walk, and then we can drift them away. Now, if we now look at this figure, we are now looking at how much light and how much charge we're going to get. This is in xenon. There's an equivalent plot for argon, of course. So now let's look at electron recoil. So we have the charge of electron recoil here in red, and we have the light of electron recoil here in blue. And you can see that at zero field, of course, you get 100% light. So all of the electrons are given very, very, very long time. They will eventually find some parent ion and recombine and produce in their own efficiency the light. Now, if you put a very tiny field here, we're talking about fields of, let's say, 100 volt per centimeter. See that the scales that we're talking about are kilovolt per centimeters. So the 100 volt per centimeter already takes a lot of the light and kills it. And then it gives the light to those free electrons, and then you can drift away the electrons. If you look at, so these are the two corresponding ones for electron recoil. Now let's look at, for instance, alphas. So these are the charges that you can get from an alpha, and this is the light that you can get from an alpha. And what you can see is that now you have to apply a very large field, let's say 2-3 kilovolt per centimeter. And what you get is a few percent of the quantars are going to be translated into charge, and you're going to lose very little in the light. What is the difference between an electron recoil and an alpha? The main difference is the density of the ionization cloud. And this, of course, allows you to think about how to differentiate between different interactions. And you can see here also with much larger arrows, it's not showing them nuclear recoil. So you can see that the nuclear recoil, if you actually put a field on it, doesn't lose much light, because again, it is much denser than the electron recoil. And it gets a small fraction of the electrons out, and you cannot get really close to 100% or even 50%, something that is very possible with electron recoil. Now, once you extracted those electrons, you have to drift them away into the somewhere that you're going to measure them. How fast are they going to drift? So you can see here that the liquid argon and liquid xenon in we'll talk about the fields soon. This is the same field that was used to kill those scintillation and extract the electrons. You're going to get several millimeters per microsecond, because this is centimeter per second times 10 to the 5. And this sets the time scale for how long it takes you to actually measure those electrons. How do you measure those electrons? This is something called proportional scintillation. So we see that if we take, now we are going to look at the what happens when you try to accelerate electrons that are traveling in the medium and give them enough energy between collisions such that they can actually excite or even ionize another electron on the way. So now we apply a field and we ask how many photons, scintillation photons, we're going to get per electron. And you can see that if the field is low, the answer is exactly 0. And then there is an onset of some process. And this process becomes stronger and stronger, the stronger the field that you have. So first of all, this is something that we already know from gas detectors, not noble gas. You know, when you apply a field, you usually lose some of the electrons. When you apply a larger field, you have a plateau of each electron producing basically 1 electron, and then you have multiplication of electrons. This is usually called the proportional signal in gas detectors. But since we're looking at proportional scintillation, this is not where we are. We would like to be somewhere here, where each electron is creating a cascade of electrons after it without multiplying itself. And this electron produces a flash of light that goes along. Now, how much voltage do we need to put? This is very simple. We have here a few volts per centimeter per torr. Now, this is in gas, of course, because we measure the pressure. The fact that we have per torr tells us that we need to multiply by approximately 10 to the 3, which is where we live. So this is a few kilovolt per centimeter. Few kilovolt per centimeter in gas would actually lead you to electrons, giving you a flash of light when they travel along this field. This is called proportional scintillation because it's proportional to the number of electrons. Each electron would give you, at a given field, would give you some yield of photons. How many photons? So here you get photons per electron per centimeter per torr. And we said with that we have 1,000 torr. So we're talking about hundreds of photons per electron. which is really nice. That means you can actually see each electron with many photons, and this is a very visible signal. This is what we will use in order to have the ionization signal measured. Now, there is a catch. The fact that this is per torr is not a coincidence. If you have liquid and you try in the liquid to have a disproportional scintillation, the voltages, the electric field that you will need grows by several orders of magnitude because of the density. And then you're not at kilovolt per centimeter, you're at sort of 100 kilovolt per centimeter. And this is extremely hard to maintain. It usually breaks down. This is not, there are trials to do that, but it's not generally working, meaning that you have to move your electrons to the gas. Now, this is a plot that shows you what the potential looks like when an electron is trying, this is now the Z direction, you can see. When an electron is trying to move from the liquid to the gas, this is the liquid and this is the gas. It needs to overcome some boundary where there is energy to surpass. Now, some of the electrons have enough momentum to cross this boundary by themselves, and then in the gas they can get accelerated and start producing the proportional scintillation. But if you just count on how much of these electrons are going to cross by themselves, you're going to only get the tail of the electrons and not most of them. This is the distribution of their momentum. So in order to compensate for this, you need to apply an electric field that will, the electric field is actually pointing left. And you have to push them to cross this field. And if you don't manage to, then only a part of the electrons are going to cross, and this is not nice. They're not crossing, so you have a smaller signal. They're not crossing, so that at some point in the future, they will become high enough, and then they will cross and produce a signal that you did not want. So this is the transfer from liquid to gas. Last thing that has to do with this, what you asked, Joseph, the combined energy scale. So to a pretty good approximation, in electron recoils, the energy can be combined by the number of photons plus number of electrons. This is really uncorrected. Just how many photons, we don't know because we don't measure all of them, and how many electrons, sometimes we do, sometimes we don't know, times this W. W is this cost per quanta, the 13 or 19 or 18 point something EV, depending on the material. And then when we look at different values of energies that we know how to measure because they come from well-known radioactive transitions, we see that the linearity between them is actually kept really nice, and we get a very good energy resolution that gets to about 1% at very high energies. This is with xenon. There are equivalent plots for argon as well. And this is something that makes us believe that this is pretty much true, the idea that the cost is per quantum. Again, this breaks down when we are talking about nuclear recoils because they lose a lot of the energy to eventually heat. Now, just a quick recap. This is the good and bad things about xenon and argon, which are going to be the focus of the next tens of minutes. So xenon, as we said, has a high light yield. It's about 13 EV per quanta. It has a low background. There are almost no radioactive isotopes of xenon. We'll talk about the few that there are. It has a high A that is good for dark matter detectors, high Z that is good for blocking gamma rays. And it has odd isotopes, which is more sensitive to, let's say, more fancy operators of interaction between dark matter and the nucleus. For instance, if you are interested in the spin of the nucleus, an odd isotope is good. On the other hand, argon is very cheap. 1% of air is argon. You can just buy it basically for free. It has amazing discrimination that we'll talk about for electron recoils and nuclear recoils because of the time difference between the singlets and the triplets. This is not existing here. And it is much easier to handle. This is a technical issue. Putting voltages, cleaning, cooling, everything is easier in argon compared to xenon. The cons of xenon, of course, is expensive. The discrimination that you can get is not relying on the time structure, but is relying on the fact that the nuclear recoils have a very different ionization density, and then the ratio between how many photons and how many electrons are emitted is different. This discrimination is a few hundreds, while this discrimination is reaching about 10 to the 8. It's hard to purify and do cryogenics. I think this is handled most of the times pretty well. Argon downsides is it has an amazing discrimination, but it's actually using almost all of this discrimination in order to battle intrinsic backgrounds that are inside the argon. This is an argon 39 that is radioactive with a beta decay, and you really have to screen it out. The threshold is high. We will talk about why. It's mostly for the discrimination and also because of the higher cost per quanta. And it has basically just argon 40 that is even A and is a bit lower than what we can get with xenon. So let's talk about how you can use the liquids in order to build a detector. So the first and simple thing you can do is build a single phase, just one big liquid chunk and many photomultipliers around it. The photomultipliers are looking for the light that is emitted from the interaction. And then you can ask yourself a few questions. First of all, how do I know where the event happened? And this is usually done by looking at the hit pattern. So each PMT gets a hit, sometimes with timing even, and you can get the approximate position. Now, why is it good? Because if you go closer to the edge of the detector, you're going to get many gamma rays and X-rays coming from the outside and creating interactions, while the center part is going to be much cleaner. So you're able to do what we call fiducialize, throw out the events that happen close to the edge. It's not perfect, but it's working. If you have a pulse shape discrimination, you can throw out, for instance, all of the gamma rays or almost all of the gamma rays and betas. And it is very simple. There are no electrodes. There is no structure. There's very little to take care of in terms of the detector. And here there is an example of the discrimination that you can do with pulse shape in argon. Here you have electron recoils from calibration and nuclear recoils from calibration. And you can see that the nuclear recoils are completely separated from the electronic recoils. The numbers here are huge. So the number of electronic recoils that will eventually look like nuclear recoils are extremely small, to the level that sometimes even calibrations don't measure one. Now, an example of this experiment is the TIP 3600. And this detector, you can see here the drawing, has an inside part that is filled with liquid argon. It has around it many PMTs. I'll talk a little bit about what is still required there. And this experiment is already running and gave nice results. This is 4 days, but actually they have better results. We look at how this detector looks. So first of all, you can see that there are some strange things here. There is some acrylic part that is surrounding the inner part. It serves, first of all, to hold the the xenon, the argon. Second, it needs to transfer the light outside. And now you can ask, why do you need to transfer the light? And the reason is that you need to not have the PMTs cold or not cold to the level of the liquid argon. And this actually costs a lot in terms of size, in terms of backgrounds. And one of the things that was most problematic eventually was a background that is unexpected, polonium-210, that was in the neck of the detector. So obviously a detector like that needs to be filled and cannot be completely closed. The pulse shape discrimination that they have shown is amazing and actually very, very optimistic for the future. I think this is a really nice experiment. You can see here the area where they are looking, which is separated nicely from the argon-39. This is, by the way, the definition that they use for the pulse shape discrimination, how much light you get in the first 100 nanoseconds and how much light you get all in all. So you can see that nuclear recoils are much faster. They give you about 70% in the first 150 nanoseconds, while electron recoils are much sparser. They take time, they produce more triplets, and they have a lot less in the first part of the event. So this is a very good example. One thing that maybe I want to emphasize is that this experiment, if you count how many tons times how much time was exposed, is the largest exposure in dark matter community, but it did not translate to the highest dark matter sensitivity. And this is for basically two reasons that we mentioned before. One is the lower A, and two is the fact that the threshold is very, very high relative to other experiments, Xenon experiments mostly. As you can see, we're talking about many photoelectrons per event in order to distinguish between electron recoils and nuclear recoils. When you start going to areas of very few photoelectrons, so you don't count that many, there is no way to distinguish between them because the statistics is not strong enough. Just to complete, there was actually also a single phase liquid xenon detector, XMAS in Japan. It has been decommissioned.
Yes. Sorry, we have a comment, I think, by Aina.
Sure, I cannot see.
Yes, yes.
Yeah, it is maybe a rather naive question, but why do you want to distinguish electron recoils from nuclear recoils? Why not consider dark matter scattering of electrons and depositing some lower amount of energy in your detector and then detecting this?
Okay, it's a good question. First of all, now we're talking about classical WIMPs. We're talking about, let's say, something that moves at 10 to the -3 the speed of light and interacts with your detector. This is what I rushed through in the beginning, but I'll say it in a clear way.
Right.
So the kinematics that you can get from interaction with an electron, if it's a free electron, an elastic scattering, you would get a few EV, which is less than producing one photon in this detector. If you have a bound electron, you can get something more interesting, and there are actually searches for electrons. This is becoming more, I will not get to that today, I don't have enough time. Some exotic searches that actually look for electron recoils. But this is not for the vanilla WIMP or the like the classical things that we're looking for.
No, of course not.
Okay.
There's another comment in the chat by Julian, who asked about the PMTs, because in Xenon they are operated at cryogenic temperature. So why does it not work for deep, I guess?
So I actually am not sure why they can't. Maybe it's a different type, but you have to remember that argon is almost 100 degrees colder than xenon. So xenon has, there is also one thing that I elegantly skipped, the fact that the argon light is actually too short wavelength to be efficiently found in photocathode of traditional PMTs. So argon community typically uses something called wavelength shifter, or TPB, that converts those high energy photons to lower energy photons that are then seen by the PMTs. But why are the PMTs for argon? I think argon has PMTs in dark side 50, which I'll show, that are working in the argon temperature, but probably not the same. These are, I have to figure out this.
Okay, thank you.
Okay. So we, as I said, there was a xenon detector that is single phase. It has been decommissioned. It is very hard to get decent discrimination in xenon as opposed to argon, which means that it's very hard to get competitive when you go to larger and larger sizes, and the background becomes problematic. It's a beautiful experiment, though. Now the leading technology in dark matter now for both xenon and argon is actually time projection chambers, and the way they work is rather simple. I will go through it quickly. If you have an interaction point somewhere in the detector, you have a field across the detector, and then when you have this interaction, you have the first scintillation light. This takes nanoseconds, and these light photons are going to be traveling around and detected in the PMTs that are either at the bottom or the top. They usually reflect off the walls and until they get caught or get lost. And at the same time, because we put an electric field, we are able to extract some of the electrons that are produced in the ionization processes, and then take them up to the top. As we said, here we have sort of a kilovolt per centimeter, and when we want to have secondary scintillation, the relevant field is about 5 kilovolt per centimeters. Plus, we need to cross the boundary from the liquid to the gas. For that purpose, we do not use the same field. We have a different stack of meshes that puts a much higher field on a few millimeters of liquid and gas. And then those electrons are pulled, and when they reach here, they meet this much higher field of close to 10 kilovolt per centimeter. They are extracted to the gas and then pulled inside the gas gap, producing those hundreds of photons per centimeter per electron. Now, those photons are being detected mostly by the top, but also by the bottom PMTs. And then we use basically the time difference between those two to tell how deep the event was, and the heat pattern on the top. So if we look, this is a view from below at the top PMT array. This tells us the X and Y, so we have a 3D reconstruction of where the event was. And as we said, since the number of photons and number of electrons, the ratio between them changes as a function of what type of interaction, what type of ionization density we have, we can differentiate between the electron recoils and nuclear recoils. This is an example of, this is just a normalized ratio between what we call S2, which is the signal that we get from the ionization, and S1, which is the signal that we got from the scintillation. And you can see that there is a nice separation between the electron recoils, which are typically background, not always, and the nuclear recoils, which are the signal that we're looking for. So what you see is, first of all, the separation here is nice, but it's not nearly as nice as the pulse shape discrimination. So typically, we're talking about 1 in a few hundred electron recoil events looking like a nuclear recoil. But then that means that you have to adjust your backgrounds in a similar way. Now, this is a quick recap. The liquid xenon community working with TPCs is very competitive. I'll go with you over a couple months in the summer of 2016. LUX experiment came up with their results that were world leading. And then during that summer, I'll tell you about LUX in a second. LUX is an experiment in the US. It's in the US in SURF. Now, the LUX and Zeppelin, which is an older collaboration, mostly from the UK, joined together and building a future detector is going to start working soon, called LZ. LZ is going to be about 7-ton TPC. Following LUX, in the same summer, Panda X, which is a Japanese experiment, came out with the result of their own, just a tiny bit better than LUX. I think that was same conference or a week later. And they are also building their own next generation experiment. They call Panda X 4 tons. This is something that I had written long time ago. They're not wasting time. This is in this slide. And then the next slide is from yesterday, where Panda X in a conference actually presented their results for Panda X 4 ton, first run. And again, they're a tiny bit better than the world leading experiment right now, which is Xenon 1 ton. And with the first preliminary run, this is just basically talk in a conference and a press release. We don't have the paper yet. I think maybe it's out today. And of course, so Panda X is now running with several tons of active detector. And I will now tell you somewhat in length about the Xenon experiment that I'm a member of and is, up until yesterday night, the leading experiment in spin dependent. Just to tell you that we're talking about the detector. The detector itself is a time projection chamber. You put the field, so the field is being regulated by those rings that are separated by resistors. Then you put the field across this TPC. You have EMTs that are looking at that on top and bottom, and this is just a detector. But the detector is this part, and then there is this part which shields it, and this part that is cut out that is servicing it. So now let's look at what's going on inside, just to show you that you have to take care of the experiment in many ways. As we said, muons are being cut out by a factor of 1,000,000 when you go underground, specifically in Versasso. But that doesn't mean they're all gone. You still need to cut data that happens when a muon makes it in this 1 in a million. And for that, you have a huge water tank that acts as a water Cherenkov detector for muons. And this is surrounding the experiment. On the outside, when you have an experiment that has to be cooled to -100 degrees, you have to keep it cold. You cannot keep it cold with anything that is touching the experiment because we don't want radioactivity. So all of the cryogenics part is outside the water tank. This is the side of the water tank. This is the actual experiment. We have to be able to recover the xenon. Xenon is extremely expensive. You don't lose it ever. And of course, you need to clean the xenon all the time. I told you that it's very nice to have noble elements because you can clean them, but that also means you need to actually clean them. There's a system taking xenon out, cleaning it, putting it back in all the time in order to keep it clean enough. And distillation, so some of the backgrounds come from parts that are noble gases as well, specifically krypton and radon. So in order to get rid of them, you cannot use any chemical means. You need to exploit some other properties. We are using their slightly different boiling point, and then this is called distillation. We distill krypton out, and in the future, or actually present, we're distilling radon out, and this has to be done online during the experiment running. And of course, you do data taking, controlling, etc. Having an experiment that is at its boiling point, has liquid and gas, is not a good idea in terms of safety, but we have to do it. The backgrounds, I'll skip it because we're running short. We have several backgrounds that contribute to the experiment. The dominant one, I think, in our case, in the xenon case, all of the xenon cases, radon 222. Radon 222 has a lifetime of 5 days. It is coming from radium, which is attached to the walls of pretty much anything in the world. Every radon atom that is produced through a radium decay will live those 5 days and will decay inside the detector. And during the chain of events following this radon decay, there is one beta emitter that is going to produce a background. This background is something we need to get rid of. Krypton 85, we said, is already cleaned before the experiment. It cannot be produced during the experiment, which is good. And watch this Xenon 136. This is a double beta decay, and the solar neutrinos that hit electrons, and they are already starting to be measurable, but not significant. The larger you grow, the more they become significant. And of course, we have neutrons that can come from uranium and thorium or alpha N, and these are, of course, very bad, and you cannot distinguish them unless you catch them with double scatter or a veto. We talked about fiducialization. In the single phase, you saw that we want to cut out the external part. Here we have an actual bucket. So we want to cut out the walls, and we want to cut out the top and the bottom. So we're only looking at the inside part. This is a top view of how many events we see inside the center. And we want to be able to discriminate between electron recoils and nuclear recoils. So you see these are calibrations. We have some overlap between them, but this is a long story. These are the results. I'm not going to go deep into that, but you see that we have many, many events in the electron recoil band. All of these, or almost all of these, are radon, basically, radon daughters that had the beta emission. And here we have some events that look maybe like dark matter and maybe not, but they're actually consistent with what we expect from the background. And you can see that this is the result that we have. This is this black line. You can see that we're working on masses between a few GeV and up to basically infinity, but here it goes up linearly. I'm sure you already discussed this. Now, as I said, we're looking for the electron recoils as well. I don't have much time, so I will just go through it extremely quickly. When we look at electron recoils, we can tell their energy by the combined energy scale. We actually found a very rare process of double electron capture. This is the equivalent opposite of double beta decay. That two electrons at the same time, this is twice weak. So this is a very, very long life process, and this is about 10 to the 22 years. Managed to measure it. It's a very nice measurement. Never mind. Something that came out from the background. So we are only looking at the background. The guy that asked about, I did see your name, sorry, about electrons. So we measure those electrons. We can say, okay, if there is something interacting with electrons, we can say, we can put a limit on how frequently it happens. There are things that could do that. There are things that are expected to do that and not interact with the nuclei. And when we look at our background and the actual data, which is those bars, we see that there is a rise at a few keV, which is strange. We're not sure what it is. The options are interesting or boring, depending on how you look at them. It could be some very, very, very small content of tritium, 10 to the minus 25 of the experiment. It could be some argon-37. This is a very rare isotope of argon. It could be wild explanations of new physics, like things coming from the center of the sun, which is conveniently the temperature of a keV. So you do expect things coming from the center of the sun to be around here, if they are produced thermally. This is an open question, and mostly we'll answer by taking this background and moving it down. And the moving it down is happening right now, not just in Xenon, but also in other experiments. There's Xenon Anton. I said we're going to have 1/10 background in the electron recoil and in the nuclear recoil. Hopefully we will see that. Two new things that should be paid attention to is, first of all, liquid xenon purification. We have a lot of xenon, and we said that we need to clean it from chemical impurities. We usually boil, clean gas, and then reliquify and put back in the detector. This is not efficient enough. In the new detector, we're actually using the liquid as it is, cleaning it and putting it back as liquid, which is much more efficient. And second, when you do that, you can do radon distillation. So we find those very few radon atoms that are going to decay in the experiment, and we detain them in radon distillation. Hopefully, this will reduce the background of the experiment to the right level. And last but not least, the neutron veto, which is trying to find neutrons that interacted once in the experiment and left it. It's sitting around the experiment. It's trying to capture them and tag them in order to not have them as background for the experiment. This is what it looked actually some time ago. I'm not going to give news about that, sorry. In the future, we're planning to build a larger experiment of about 50 tons to reach the famous neutrino floor. Actually, I want to move to, yes, I see hands. I actually see a hand. Beth Long.
Yeah, I had a question about the backgrounds and the purification that two slides ago, I think it was. Yeah. So I was wondering, once you've reduced your background and you've done these new purification techniques, will you have information on how much contaminants were in your detector in the first place? So will you then be able to reduce, will you be able to take that background away from the data that you've already taken and improve your sensitivity?
All right, so there are several levels to that. I'm assuming you're not talking about chemical impurities. They are a nuisance in terms of running the detector because they capture electrons, but they do not produce, generally speaking, they don't produce backgrounds that go into the data.
Yeah, I was meaning like the radon content and stuff like that.
So radon, typically, radon and other elements, we have some orthogonal ways of assessing how much there is. When you look at this line here, then the background that we have actually has the roots of that is how much radon we have in there and what is the spectrum that you expect from radon. How much in xenon anton we're going to have, just as an example, neutrinos from the sun. We're going to have a little bit of krypton, gamma rays from the outside. All of those we assess separately, each one, and with their respective uncertainties, of course, and they're put into the model of the background. Now, most of them, so now I'm talking about, in this slide specifically, I'm talking about looking at the background and trying to find weird stuff in the background. What we typically do is here, you can see here this circle is, this is where we look for the WIMPs, and those backgrounds are all going to be around here. So the level of understanding that we need on the background in order to do the WIMP search is much, much smaller than what we would need if we want to see if there is something weird in the background. I hope I'm saying it in a...
Yeah, that's really clear.
Okay, but it's true that once we start looking at how the background is behaving, the first major task is to figure out all of the components. And we do that with, so radon, for instance, you can, I said there is a chain. So there are like 10 different interactions that happen before you have the actual background that bugs us. And we try to tag them and find them and see how they behave and how they behave over time. All of them, of course, this is it's a major task.
Okay, thank you very much.
Okay. I have very little time. I'll tell you about argon. So argon is, as we said, extremely useful in cleaning the electron recoils, because you can tag them at 10 to the minus 8 errors and see the region of interest. So here you can see the dark side 50, which is also in Gran Sasso. It's a smallish detector compared to today's standards. It's a TPC inside this tiny box and surrounded by a liquid scintillator that is used for a neutron veto. And you can see that the background here actually never leaks to the actual data region or region of interest. And this is even without using the fact that you have S1 and S2. This is just the fraction of photons in the prompt scintillation light. Again, the major problem of argon is that the threshold is higher. So dark side 50 is now growing into dark side 20K. Dark side 20K is supposed to be about 20 tons of xenon, argon. And the problem is that the discrimination is better than 10 to the 7. It's claimed to be about 10 to the 8. But the problem is that the argon 39 that is in atmospheric argon is even higher than that. So this is not enough. So the argon community started mostly with the dark side, is working on harvesting underground argon that has been, so the argon 39, I think, is about 200 years lifetime. If you have something that was under the ground for thousands of years or millions of years, you can get a much lower content of radon, of argon 39, and they are doing that. The way they extract it is liquefying it underground from air that is extracted. This is the size of the Eiffel Tower and the size of their liquefaction and distillation. It's huge. And argon is already trying to grow to the next level, I should say. So right now, if you look at the current reach, the sensitivities of argon detectors, this dark side 50 and deep 3600, they are around here. They are already trying to get argon. This is a log scale, right? We're talking about 4 orders of magnitude. 3,000 ton years. This is a collaboration of basically all of the argon people in the world, or almost all of them. They need to get that much argon. They need to get that argon from underground. They need to choose the technology and the place. And this is all ongoing. I hope this will be a successful endeavor. This is very challenging. One thing that is funny to look at is that the units that are down here are not GeV, but TeV, and this is because argon, as we said, has the shortcoming mostly is that the low energy or low mass sensitivity is very limited. I'll just say a few words. If you want to discover low mass dark matter, you would need to see something that is typically emitting very few photons. There are a few ways to do that. This is Joseph for you. First of all, there are two interesting interactions that could happen when you interact with the nucleus. But instead of interacting with the nucleus and kicking a nucleus, you can actually emit a gamma ray. And we said that the gamma ray emits much more, many more quanta compared to the nucleus. And this is also inelastic, so you can transverse some limit of energy and momentum. So the first is a Bremsstrahlung, where you have a final state of chi, a gamma ray, and the nucleus. And second is something called the Migdal effect. When you kick a nucleus and you move it inside its electronic cloud, actually the new states that are with the removed nucleus have some overlap between higher orbitals and the electrons that are originally in their unperturbed orbitals. And with some amplitude, you can actually move an electron up. And if electron is moved up to a higher orbital, it will go down and emit a photon. And this photon can be discovered. You can see that we're talking about electron recoils now, and this is not something we can discriminate, but we can look for them and we can say how many we saw. The good thing is that they don't happen a lot in the detectors, so you can actually do some analysis. Lux did that in 2018. DarkSide 50 did, okay. Lux did it in 2018. I actually have it. I have something missing here. Sorry. And the idea is that you can reach now very low masses, below 1 GeV. You can see that the only thing that are competing with that are going to be crystals. This is the next talk. And this is something that can be pushed even lower than that, but we don't have time. I'll just say that you can, I told you about time projection chambers. Usually the light is extremely faint, but you do see an electron. Each electron gives you hundreds of photons, so you can collect them one by one and count them. If you give up the S1, you have a lot of background, but on the other hand, you have a sensitivity to very, very low energy depositions, so you can do this analysis. This has been done for about 10 years now. Which has its downsides of not understanding the background and upsides of very high sensitivity. And last but not least, I'll tell you for 1 minute about helium. Helium, as you know, is much lighter than argon and xenon. And the fact that it's lighter gives the recoil energy spectrum a very, very large boost to high recoil energy. So you can see here that a GeV particle can kick it to about a keV of energy. And this means that if you can build a helium detector, a liquid helium detector, you can find lighter dark matter. It hasn't been done, but in principle, this is possible. And the most intriguing, I think, part is that liquid helium, if you cool it enough, becomes superfluid. And a superfluid helium has many properties that can be used in order to detect dark matter interactions, reject backgrounds, and do it on a single atom level. So you can break the superfluid and have the measured particle coming out with an extra boost that you get when you leave the superfluid continuum.
Ranny, we have one raised hand, if I may interrupt.
I think I will, you know what, I will end here, I think, because my time is up, I think.
Okay, okay.
Right? And go to, this is a thing we did not cover. By the way, this I would follow. This is Dan McKinsey and Scott Hertel are doing that, and they're, it's very interesting and intriguing. Hasn't been demonstrated yet in actual detector, but I think we'll go down to MEV scale dark matter sensitivity, which is completely missing from the map. And this is my summary, and I'll just leave the summary for you to read and answer questions. Thank you. Sorry,